You can take almost anything and cut it in half. Cut a sheet of paper and you get 2 smaller pieces. Cut one of those and you get pieces smaller still. In your mind, the cutting never has to stop. Halfway, then halfway again, forever, down past atoms, past the parts inside them, with no last door. But the universe seems to have a last door. There is a length so small that the words smaller than this may stop meaning anything. And when our best theories try to describe what happens down there, they stop giving answers and start giving nonsense. That smallest size is called the Planck length, and the place it marks is the Planck scale. We're going to walk down to it slowly, one step at a time, starting from things you already know. The real question underneath all of it is simple. Is there a bottom to how small the world can get? If quiet, unhurried walks through big ideas are your kind of thing, take a second to subscribe and we will begin. Pick up a sheet of paper and tear it in half. You now hold 2 smaller pieces, each one thinner and lighter than what you started with. Tear one of those in half and you have something smaller still. There is nothing strange about this. You have done it your whole life, with paper and bread and string and time, and somewhere in the back of your mind the tearing feels like it could go on forever. Half, then half again, smaller and smaller, with no reason to ever stop. That feeling is one of the oldest ideas in human thought. More than 2,000 years ago in Greece, a thinker named Democritus followed it the other way. He imagined cutting a piece of matter again and again, and he asked what would happen if you never reached an end. It seemed absurd to him, so he proposed that the cutting must stop. At the bottom, he said, you would reach a piece that could not be cut at all. He called it the atom, from a word that simply meant uncuttable. He was right that there is structure down there, and beautifully wrong about the details. The thing we call the atom today can be cut. Inside it sits a tiny dense nucleus, and around that nucleus a haze of electrons. Crack the nucleus open and you find protons and neutrons. Look inside those and you find quarks, held together by a force so strong it has no off switch. At every step the world got smaller, and at every step so far there was more world underneath. So the honest question is the one Democritus started with. When you keep zooming in, when you keep cutting, does the smallness ever bottom out? Is there a smallest possible size, a last door past which the word smaller stops meaning anything at all? Or does the world simply keep going down, structure inside structure, with no floor? For most of the history of science, the safe answer was that the world keeps going. Every time someone thought they had found the smallest thing, a sharper instrument found something smaller. The lesson seemed clear. There is no bottom, only better microscopes. To claim a smallest length would have sounded like a failure of imagination, a refusal to look harder. But in the last century, something changed. It did not come from a microscope. No one saw the bottom. Instead, 3 of the deepest facts we know about the universe were laid side by side, and when you combine them, they point to a number, a single length, fantastically small, that seems to mark a genuine edge. Not the edge of what we can build, but the edge of what our physics can even describe. Below that length, our 2 best theories of the world stop agreeing with each other and stop giving sensible answers and start handing back nonsense. That length has a name. It is called the Planck length, after the German physicist Max Planck, who stumbled onto the idea more than 120 years ago without fully knowing what he had found. The realm it marks is called the Planck scale, and the strange thing about it is that we did not discover it by going there. We have never been anywhere close. We worked it out from constants we already trusted, the way you might work out the height of a mountain from its shadow without ever climbing it. Over the next stretch of this walk, we're going to build that number up slowly, from pieces you can hold. We will start with 3 plain facts about light, gravity, and the quantum world. We will see how they fit together into a ruler, and then we will follow that ruler all the way down to the last door and ask what really happens when we try to open it. The climb starts with the first of those 3 facts, and with the speed of a beam of light. To get to the bottom of the world, you need 3 numbers. Not 3 theories, not 3 equations, just 3 plain measurements that the universe seems to have written into itself. Each one was found by a different person, in a different century, chasing a different question. None of the 3 had any idea their number would one day be combined with the others, and yet when you finally lay them next to each other, they snap together like 3 keys cut for the same lock. The first number is the speed of light. Light does not travel instantly. It is fast, almost beyond imagining, but it takes time to cross a room, time to cross a planet, time to cross the gap between stars. There is a fixed top speed in the universe, the same for everyone, everywhere, and light moves at exactly that speed. We write it with the letter C. It is roughly 300,000 kilometers every second, fast enough to circle the Earth 7.5 times before you finish saying the word fast. The second number is the strength of gravity. Every mass pulls on every other mass, the Earth on the Moon, the Sun on the Earth, your body on the page in front of you. But gravity is astonishingly weak. The pull between 2 everyday objects is so faint you can spend a lifetime never noticing it. There is a constant that says exactly how strong this pull is, how much force you get for a given pair of masses at a given distance. It is named after Isaac Newton, who first wrote the law of gravity down, and it is usually called Big G. The third number is the quantum of action. This one is the youngest and the strangest. It says that nature comes in tiny indivisible portions, that energy and motion at the smallest scales are not smooth but grainy, doled out in fixed minimum amounts. The size of that grain is set by a number called Planck's constant, written with a small h. It is unimaginably small by everyday standards, which is exactly why you never feel the graininess in ordinary life. The world looks smooth to you for the same reason a beach looks smooth from a distance, even though it is made of separate grains of sand. So there they are, the speed of light, which ties space and time together, the gravitational constant, which sets the strength of the pull that shapes planets and galaxies, and Planck's constant, which sets the size of the quantum grain. 3 numbers from 3 corners of physics that almost never meet. Light belongs to relativity. Gravity belongs to the shape of space. The quantum grain belongs to the world of the very small. For a long time, these were treated as separate kingdoms with separate rulers. Each of these numbers is what physicists call a fundamental constant. It does not seem to depend on where you are or when you measure it. It is not the speed of this particular beam of light or the pull of this particular planet. It is a property of the universe itself, as fixed as we have ever found anything to be. You can change the units you write them in, swap kilometers for miles, but the physical truth underneath stays the same. What Max Planck noticed near the end of the 19th century was that these 3 numbers carry units. The speed of light is a length divided by a time. Newton's constant mixes mass and length and time in its own way. Planck's constant mixes them in another. And if you have 3 numbers that each blend length, mass and time differently, you can play them against one another until the units of mass and time cancel out, and you're left holding a pure length. A length built from nothing but light, gravity, and the quantum. Before we build that length though, we need to understand each of the 3 numbers on its own, beginning with the strange and stubborn speed of a light. For most of human history, people assumed that light was instant. You open your eyes, and the world is simply there. A lamp lit across a valley seems to arrive at your eye the moment it flares. It feels like seeing has no delay at all. So the idea that light might take time to travel was not obvious. It had to be discovered, and the discovery came from the sky. In the 1600s, a Danish astronomer named Ole Romer was watching the moons of Jupiter. Jupiter has 4 large moons, and the innermost of them, called Io, swings behind the planet on a clock-like schedule, vanishing into shadow and reappearing again. Romer noticed something odd. When the Earth was on the near side of its orbit close to Jupiter, the eclipses of Io came a little early. When the Earth had swung around to the far side, they came late. The Moon was not changing its schedule. The light from it simply had farther to travel, and that extra distance took extra time. From the size of the delay, Romer worked out that light was fast but finite. It was the first real measurement of the speed of light, made by watching a tiny moon blink. 2 centuries later, the picture deepened. A Scottish physicist named James Clerk Maxwell was studying electricity and magnetism, 2 forces that had always been treated as separate. He found a set of equations that wove them together into one thing, the electromagnetic field. And buried in those equations was a speed, the speed at which a ripple in that field would travel. When Maxwell calculated it, the number came out matching the measured speed of light almost exactly. That was the moment light stopped being a mystery of its own and became something deeper. Light was a wave in the electromagnetic field, and its speed was set by the basic constants of electricity and magnetism. But the real shock came from a young patent clerk named Albert Einstein. He took Maxwell's speed seriously, more seriously than anyone had dared. He asked a simple question. What if the speed of a light is the same for everyone, no matter how they are moving? Picture chasing a beam of light. Common sense says that if you run after it fast enough, the beam should appear to slow down relative to you. The way a car beside you on the highway seems to drift backward as you speed up. Einstein proposed that light refuses to play this game. Run as fast as you like and the beam still races away from you at the very same speed. Hold that thought, because it cannot be true unless something else gives way. If the speed stays fixed no matter how you move, then the things you used to think were fixed, distance and time themselves, must bend instead. Moving clocks tick slow. Moving rulers shrink along their direction of travel. The faster you go, the more space and time rearrange themselves to keep the speed of light the same for you and for everyone. Space and time turn out to be 2 faces of one thing, woven together, and the speed of light is the thread that stitches them. This is why c shows up far from anything to do with light. It is not really the speed of a beam. It is the conversion rate between space and time, the universe's exchange rate between meters and seconds. It is also the cosmic speed limit. Nothing carrying information or mass can be pushed past it, no matter how hard you shove, because reaching it would take infinite energy. So the first of our 3 numbers is more than a measurement. It is the rule that binds space to time and caps how fast anything can move. Keep it in your pocket. The second number is far gentler and far harder to feel, and it was first pinned down by a very shy man weighing the earth in a garden shed. Of the 3 numbers we need, gravity gives us the one that is easiest to feel and hardest to measure. You feel gravity in every step. It is the pull that holds you to the floor, that brings a dropped cup to the ground, that keeps the moon circling the earth and the earth circling the sun. Of all the forces in nature, it is the one that runs our daily lives. So it comes as a surprise to learn that gravity is, by an enormous margin, the weakest force there is. You can prove that to yourself with a small magnet. A cheap fridge magnet weighing a few grams can pick up a paperclip against the pull of the entire planet beneath it. The whole Earth, with all its mass, is losing a tug of war to a toy. That is how feeble gravity is compared to the other forces. It only seems mighty to us because there is so much of it gathered in one place. A planet is a vast pile of matter, and every speck of it pulls. But the pull from any single piece is almost nothing. This weakness made gravity very hard to measure between ordinary objects. Newton wrote the law in the 1600s. He said that any 2 masses attract each other with a force that grows with the masses and fades with the square of the distance between them. The law was beautiful and it worked, predicting the orbits of the planets with stunning accuracy. But there was a number missing from it, a constant that fixes the actual strength of the pull. Newton could describe how gravity falls off with distance, but he could not say how strong it was in absolute terms. To find that, someone had to measure the faint attraction between 2 weights you could hold in your hands, and that was thought to be almost impossible. The man who did it was an English aristocrat named Henry Cavendish. Cavendish was brilliant and almost painfully shy. He was so uncomfortable around people that he had a separate staircase built in his house to avoid meeting his own servants, and he gave them instructions by note. He cared nothing for fame and published only a fraction of what he discovered, but he had the patience and the wealth to chase a measurement that no one else could manage. Near the end of the 1700s, Cavendish built a device of exquisite delicacy. He hung a light rod from a thin fibre with a small lead ball at each end, so the rod could twist freely like the needle of a compass. Then he brought 2 large lead spheres close to the small ones. The faint gravity between the big balls and the small balls tugged the rod, twisting the fibre by a tiny angle. By measuring that twist, he could measure the force, and from the force, the strength of gravity itself. He worked in a sealed shed to keep out drafts and changes in temperature, watching the rod through a telescope from outside so that his own body heat would not disturb it. From that whisper of a twist, Cavendish calculated the density of the Earth, and so, in effect, weighed the entire planet. Tucked inside his result was the number we now call the gravitational constant, big G, the strength of gravity written into the fabric of the world. It is a fantastically small number, which is exactly why the experiment was so hard. The pull he was measuring was smaller than the weight of a falling speck of dust. That smallness matters for our story. Because gravity is so weak, its constant is tiny, and that tiny value will push our final number to an almost unimaginable extreme. Keep big G in your pocket beside the speed of light. The third number comes from a different world entirely, from the glow of hot objects and the birth of the quantum. There is a number that every blacksmith has seen with their own eyes, long before anyone could explain it. Heat a piece of iron, and it begins to glow. First a dull red, then a brighter orange, then a yellow that whitens as it gets hotter still. The colour of a glowing object tells you its temperature. The same thing happens with the coils of a toaster, with the filament of an old light bulb, with the surface of a star. Hotter things glow bluer, cooler things glow redder, and this rule holds across the whole universe. In the late 1800s, physicists tried to explain this glow with a theory they had, and they failed badly. They pictured the light coming from tiny vibrating charges in the hot material, each able to ripple at any frequency it liked. When they added up all the possible ripples, the math made a disastrous prediction. It said that any warm object should pour out an infinite amount of energy at the blue and ultraviolet end of the spectrum. By that reasoning, the gentle warmth of a fireplace should blast you with a lethal flash of ultraviolet light. Clearly that does not happen. The theory was not slightly off. It was catastrophically wrong, and the failure was so glaring it earned a dramatic name, the ultraviolet catastrophe. The man who solved it was Max Planck, a careful and deeply conservative German physicist who had no taste for revolution. Planck was a traditionalist. He revered the established laws and trusted them. So when he finally cracked the problem, in the year 1900, he did it almost against his own instincts, and he later called the step an act of desperation. Planck found that he could match the glow of hot objects perfectly, but only by making one strange assumption. He had to suppose that the vibrating charges could not give off energy in any amount they pleased. Instead, they could only release it in discrete chunks, in fixed minimum portions. Energy at this scale came in packets, like coins of a currency that has a smallest coin and nothing finer. You can have 1 packet or 2 packets, but never a packet and a half. The size of each packet depended on the frequency of the light, and the link between them was a new constant, a number Planck introduced to make the math work. We call it Planck's constant, written with a small h. It is the size of the quantum grain, the smallest unit of action in the universe. With that one assumption, the infinite ultraviolet glow vanished. High-frequency light needs large energy packets, and at any given temperature there is rarely enough energy on hand to make those big packets, so the glow naturally tapers off at the blue end instead of exploding. The catastrophe was gone. Planck had stumbled onto the foundation of quantum theory, though he did not embrace it at first. He hoped his energy packets were a mathematical trick, a temporary scaffolding that a deeper, smoother theory would eventually remove. It was Einstein, a few years later, who took the packets seriously as real, showing that light itself arrives in quanta we now call photons. The grain was not a trick, it was how the world is built. So the third number is Planck's constant, the measure of how grainy reality is at the smallest scale. It is what separates the quantum world from the smooth world of our senses. The grain is so fine that ordinary life never reveals it, the way the dots in a printed photograph hide until you press your eye to the page. Now we hold all three numbers, the speed of a light that binds space and time, the gravitational constant that sets the weakness of gravity, and Planck's constant that sets the size of the quantum grain. Planck himself was the first to notice what happens when you let these three numbers meet. Max Planck had given the world a new constant, and he immediately did something with it that almost no one else would have thought to do. He started dreaming about units of measurement. This sounds like a dry place to find wonder, but stay with it. Think about how we measure length. We use the meter. But where did the meter come from? Originally it was defined as 1/10,000,000th of the distance from the equator to the North Pole, measured along a line running through Paris. That is a perfectly good length, but it is also completely accidental. It depends on the size of the Earth, on a particular line of longitude, on a committee in France in the 1790s. A civilization on another planet would never arrive at the meter. They have their own world, their own history, their own arbitrary choices. The same is true of the second, born from dividing up the day, and the kilogram once tied to a lump of metal kept in a vault near Paris. All of our everyday units are human stories. They are tangled up with the size of our planet, the length of our day, the shape of our hands. There is nothing wrong with this for daily life. But it bothered Planck. He wanted to know if there was a deeper way to measure things, a set of units that did not depend on us at all. His idea was simple and bold: build units out of the fundamental constants of nature and nothing else. The speed of light, the gravitational constant, and his own new constant were not human inventions. They were not tied to the Earth or to any particular planet or star. They appeared to be the same everywhere in the universe, written into its basic operation. If you built your units from those, then any intelligent being anywhere, on any world, in any era, studying the same physics, would arrive at exactly the same units you did. They would be truly universal, a common language between minds that had never met. Planck found the way to do it. As we noted, each of his three constants carries a different blend of length, mass, and time. The speed of light is length over time. The gravitational constant folds in length, mass, and time in its own combination, and his quantum constant folds them in yet another. With three independent blends, you have enough freedom to isolate each basic quantity on its own. You can juggle the three constants until everything cancels except a pure length, then juggle them another way and get a pure time, another way again, and out comes a pure mass. The units fall out of the constants like answers from a well-posed puzzle. Planck was delighted by this. He wrote that these units would keep their meaning for all times and for all cultures, even non-human ones, and could therefore be called natural units. He saw them as a kind of permanent measuring stick, one the universe itself had laid down, free of any trace of Earth or humanity. In a paper from the late 1890s, before he'd even finished his work on the glowing of hot bodies, he laid these natural units out. What he could not have known was how strange the numbers would turn out to be, or what they would come to mean. To Planck, the natural units were a philosophical jewel, a beautiful way to measure the world from the universe's own point of view. He did not see them as the marker of an edge where physics fails. That meaning would only become clear much later, as relativity and the quantum grew up and began, at the smallest scales, to clash. For now, hold on to the idea. Three universal constants, three blends of length, mass, and time, and a recipe for distilling from them a length, a time, and a mass that belong to no planet and no people, but to the cosmos itself. In the next step, we will actually run that recipe and watch the ruler take shape. Let us actually build the ruler. We have three constants in our pocket: the speed of light, which we write as c, Newton's gravitational constant, big G, and Planck's constant, the quantum grain, which physicists usually use in a slightly streamlined form, written with a special symbol and called h-bar, the same idea as Planck's h, with a fixed factor folded in. Do not worry about that detail. What matters is the recipe. The trick rests on units, on the kinds of quantities each constant carries. Think of it like cooking. Imagine you have 3 ingredients, and each one is a mixture of 3 basic flavors. Call them length, mass, and time. The speed of light is mostly length and time, since a speed is a distance covered in a time. Newton's constant has its own recipe of all 3. Planck's constant has yet another. Because the 3 mixtures are different, you can combine them in just the right proportions to cancel out the flavors you do not want, and keep only the one you do. Suppose you want a pure length, and only a length, with no mass and no time left over. There is exactly one way to multiply and divide your 3 constants so that mass and time vanish, and a length survives. You take Planck's constant, multiply it by the gravitational constant, divide by the speed of light raised to a power, and then take the square root of the whole thing. When the dust settles, the units of mass and time have eaten each other, and all that remains is meters. That number is a real, specific length, fixed by the constants of nature. It is the Planck length. Do the same juggling with a different goal, and you can isolate a time. Multiply and divide the same 3 constants in another proportion, take a square root, and out comes a quantity measured in seconds. That is the Planck time. Choose yet another combination, and the leftover flavour is mass, giving you a quantity in kilograms. That is the Planck mass. From those 3 you can spin off others: a Planck energy, a Planck temperature, a Planck charge, each one built from the same handful of constants. Notice what has happened. We did not measure these quantities. We did not build a tiny ruler or a tiny clock. We never went anywhere small at all. We simply took 3 numbers we already trust, 3 numbers measured in completely separate experiments by completely different people, and we asked what length, what time, and what mass they imply when combined. The answers are forced. Once you accept the 3 constants, the Planck units are not a matter of opinion. They are baked in. This is one of the quietly astonishing things in physics. You can reach a conclusion about the very smallest scales of reality without any instrument that can see down there, purely by taking the rules of the universe at their word and following them to their logical end. It is like learning the depth of an ocean trench by combining the pressure at the surface, the density of the water, and the temperature without ever lowering a line. The constants do the measuring for you. There is also a deeper hint hiding here, one we will return to. The Planck length is special because it is the only length you can build from these 3 constants. And those 3 constants are the signatures of 3 great theories. The speed of light belongs to relativity, the theory of space and time. The gravitational constant belongs to Einstein's gravity, the theory of curved space-time. And Planck's constant belongs to quantum mechanics, the theory of the very small. A length built from all 3 is a length where all 3 theories must speak at once. That is exactly the place we are heading, and exactly the place where the trouble begins. But first, let us look at the length itself, and feel just how small it really is. Now we can finally hold the first answer in our hands. Run the recipe for a length, plug in the speed of a light, the gravitational constant, and Planck's constant, and out comes a number, the Planck length. And it is small in a way that ordinary words barely reach. Let me try to give it to you in steps you can climb down. Start with something you know, a meter, about the length of a long stride or the height of a kitchen counter. Now go smaller. A millimeter, the thickness of a credit card, is 1,000 times shorter than that meter. Smaller again, to a micron, the size of a bacterium, 1,000 times shorter still. Smaller again to a nanometer, where a few atoms sit side by side. Keep going, past the atom, past its nucleus, down to the proton, one of the particles inside that nucleus. The proton is about 100,000 times smaller than a whole atom. You're now unimaginably deep, far below anything you will ever see or touch, and you are nowhere near the Planck length yet. From the proton, you still have to go down by another factor of about 100 billion billion. That is a 1 followed by 20 zeros. The Planck length is roughly that many times smaller than a proton. To say it another way, a proton is to the Planck length as a small town is to a single atom inside it. The gap between the proton, already one of the tiniest things we can study, and the Planck length below it is itself one of the widest gaps in all of physics. We have built machines that can probe down toward the proton and a fair way inside it. We have never come remotely close to the Planck length, and with any technology we can presently imagine, we never will. Written out as a fraction of a meter, the Planck length is a decimal point followed by 34 zeros and then a few digits. It is so far below the scale of any experiment that for most of physics it simply never comes up. The particles in our biggest colliders, smashed together at enormous energies, still only resolve distances trillions of times larger than this. The Planck length sits at the very floor of the conceivable. Here is what makes that number more than a curiosity. It is not just small, it appears to be a kind of limit on the very meaning of length. Above this scale, our ideas of distance and position work fine. You can ask where something is and how far it is from something else, and get a sensible answer. As you approach the Planck length, those questions start to wobble, and below it, if our reasoning holds, the questions may stop making sense at all. The idea of a definite point in space, a sharp location with a smaller neighbourhood around it, seems to dissolve. There may be no such thing as a distance shorter than this, not because our rulers are too crude, but because there is nothing there to measure. That is a strange and heavy claim, and we have not earned it yet. We will earn it later, step by step, by combining the uncertainty of the quantum world with the gravity of dense objects. For now, just sit with the size. The Planck length is the shortest length that the constants of nature allow you to build, and it appears to mark the boundary of the smallest world. Length is only the first of the Planck units, and on its own it is hard to picture, since we cannot see anything close to that scale. But length is tied to time through the speed of light, and the Planck time turns out to be just as extreme, and in some ways even easier to feel. It is the time it takes light to cross a single Planck length, the shortest tick the universe seems to allow. If the Planck length is the shortest distance, then there is a shortest time to match it, and you can almost reach it by thinking about light. We have one firm rule from earlier: nothing moves faster than light. Light is the fastest messenger there is, so the quickest possible way to cross any distance is to send a flash of light across it. Anything else is slower. Now ask a simple question. How long does it take light to cross one Planck length? Light is fast and the Planck length is absurdly small, so the answer is a span of time so short it has no rivals. That span is the Planck time. It is, in a real sense, the time it takes the fastest thing in the universe to cross the smallest distance in the universe. You cannot get a shorter, more fundamental tick than that. Any event briefer than this would require something to cross less than a Planck length, and that may simply not mean anything. The number is hard to grasp, so let me turn it around to give you a feel for it. Take a single second, the time of one heartbeat, or one spoken word. Inside that 1 second, how many Planck times tick by? The answer is a number so large it dwarfs almost any count you have ever met. There are more Planck times in a single second than there have been seconds in the entire history of the universe. The universe is around 14 billion years old. Count every second since the Big Bang, every tick of every clock across all of cosmic history, and you still fall hopelessly short of the number of Planck times that pass while you blink. The fine grain of time is that fine. This gives the Planck time a special role in the story of the cosmos. When we run the history of the universe backward, the galaxies draw together, the matter grows denser and hotter, and everything we know is squeezed toward a single blazing moment near the beginning. We can run our theories back through the first minutes, the first seconds, the first fractions of a second after the Big Bang with real confidence, but there is a wall we cannot pass. When we reach 1 Planck time after the beginning, our physics gives out. We can describe what the universe was doing 1 Planck time after its birth. We cannot honestly say what happened before that, because the theories we would need stop working. That earlier sliver, the first Planck time, is the oldest closed door in cosmology. It is worth pausing on how the Planck length and the Planck time hold hands. They are not two separate facts. They are tied together by the speed of light, the same thread that stitches space to time. The Planck length is a distance. The Planck time is how long light takes to cross it. Multiply the Planck time by the speed of light, and you get the Planck length right back. They are two views of one thing, a smallest cell of space and a smallest tick of time, locked together by the cosmic speed limit. There is a tempting picture here, and we should hold it gently rather than grab it. It is tempting to imagine space-time as a grid, divided into tiny boxes 1 Planck length wide, ticking forward in steps 1 Planck time long, like the pixels and frames of a cosmic screen. That picture may even be close to right, but we do not actually know that space-time is chopped into neat pieces, and we will see later that the honest answer is still open. For now, the safe statement is narrower. Below the Planck length and the Planck time, our current physics has nothing reliable to say. 2 of the 3 Planck units have turned out fantastically small, the length and the time. You might expect the third, the mass, to follow the pattern and be the tiniest mass imaginable. It does the opposite, and that surprise is the next door we open. Here is where the pattern breaks, and the break is the interesting part. The Planck length is the smallest length. The Planck time is the shortest time. So you would naturally expect the Planck mass to be the smallest mass, some impossibly tiny weight far below a single atom. That is the obvious guess. It is wrong, and being wrong about it teaches us something. Run the recipe for mass, combining the 3 constants in the proportion that leaves kilograms behind, and the number that comes out is not tiny at all. By the standards of the particle world, it is enormous. The Planck mass is about 20 micrograms. That may not sound like much in everyday terms, and indeed it is small for a person. But picture it the right way. It is roughly the mass of a flea's egg, or a single grain of fine pollen, a speck just barely too small to see clearly. You could hold many of them on a fingertip. Now feel the strangeness. A speck of dust is, by ordinary standards, almost nothing. But compare it to the world of particles. A single proton is fantastically light. The Planck mass is heavier than a proton by something like 10 million billion times. In the realm of fundamental particles, where masses are measured in the faintest whispers, the Planck mass is a giant, a monster, a quantity wildly out of scale with everything around it. The smallest length and the shortest time came out unimaginably small. The corresponding mass came out shockingly, almost absurdly large. Why does this happen? The answer lies in the weakness of gravity, the very thing we met when Cavendish weighed the Earth. Gravity is feeble. Its constant, big G, is a tiny number. And in the recipe for the Planck mass, that tiny gravitational constant sits underneath, in the denominator, where small numbers make the result large. Because gravity is so weak, you need a relatively hefty lump of mass before its gravity becomes as important as its quantum behaviour. The Planck mass is precisely the mass at which an object's gravity and its quantum nature become equally strong, where the pull it exerts and the fuzziness it carries meet on equal terms. And because gravity is so weak, that crossover does not happen until you reach a mass far above any single particle, all the way up at the scale of a speck of dust. This is the deep reason the Planck scale is so hard to reach. For everything we normally study, gravity is utterly negligible. The gravitational pull between 2 electrons is so much weaker than their electric repulsion that physicists simply ignore it, and they are right to. Quantum theory and gravity almost never matter at the same time. Quantum theory rules the small and light. Gravity rules the large and heavy. They live in different neighbourhoods and rarely visit. The Planck mass marks the one address where both must speak at once, and it sits far from anything we can build. There is a haunting image hidden in this number. Imagine taking the Planck mass, that speck of dust, and squeezing it down into a region the size of the Planck length. A speck of dust crushed into a volume trillions of times smaller than a proton. If you could do that, the object's gravity and its quantum fuzziness would both be at full strength in the same tiny place. As we will see in a few steps, an object like that is no longer just a heavy speck. It is something closer to the smallest possible black hole, a knot where gravity and the quantum collide. That collision is the whole reason physics breaks down at this scale, and the Planck mass is our first glimpse of it. We have a length, a time, and a mass. From the mass, with the speed of light, we can build an energy and a temperature, and those carry the furnace heat of the early universe. We have built a length, a time, and a mass. With those in hand, two more Planck quantities follow almost for free, and they carry the heat of creation in them. They are the Planck energy and the Planck temperature. Start with energy. We have a relationship that ties mass and energy together, the most famous equation in all of science, Einstein's statement that energy equals mass times the speed of light squared. It says that mass is a frozen form of energy, and that even a small amount of mass holds a vast store of energy, because the speed of light squared is such a huge multiplier. So once you have the Planck mass, you can find the Planck energy simply by unlocking the energy hidden in that mass. Take the Planck mass, that speck of dust, and ask how much energy it represents. The answer is startling. The Planck energy is roughly the energy of a bolt of lightning, or the chemical energy stored in the gasoline filling a car's tank. By everyday standards, that is a lot of energy, but not unimaginable. You have seen lightning. You have filled a tank. Here is the part that bends the mind. The Planck energy is not spread across a storm or a fuel tank. It is the energy you would have to pack into a single subatomic particle to probe the Planck scale. A whole tank of gasoline's worth of energy, concentrated into one particle far smaller than an atom. That is the scale of violence the Planck world demands. This is why no machine on Earth can reach the Planck scale by brute force. Our greatest particle accelerator, the Large Hadron Collider, accelerates protons to enormous energies and smashes them together. Yet the energy it gives each particle is about 1,000 trillion times smaller than the Planck energy. We will come back to just how hopeless the gap is. For now, hold the picture. To touch the Planck length directly, you would need to put the energy of a lightning bolt into a single particle, and nothing we can build comes anywhere close. Now turn energy into temperature. Temperature at bottom is just a measure of how much energy the particles in something carry as they jiggle and fly about. Hot means fast and energetic. Cold means slow and calm. So a Planck energy crammed into a particle corresponds to a temperature, and that temperature is the highest meaningful temperature in physics. It is called the Planck temperature. The number is almost beyond description. The centre of the Sun, where hydrogen fuses into helium, sits at around 15 million degrees. That is hot enough to power a star. The Planck temperature is hotter than the core of the Sun by a factor of about 10,000 billion. There is no furnace, no explosion, no star or supernova in the present universe that comes anywhere near it. The only time reality itself is thought to have reached the Planck temperature was at the very first instant of the Big Bang, in that first Planck time we spoke of, when the entire universe was packed into a space smaller than anything we can picture and seethed at this unthinkable heat. That is why the Planck temperature is sometimes called the temperature of the beginning. It is the furnace edge of physics, the hottest the equations will allow before they break. Push past it, try to describe something hotter, and the theories stop returning sensible answers, just as they do below the Planck length. The Planck energy and the Planck temperature are the high walls of the same room whose floor is the Planck length, all of them marking the single boundary where our physics ends. Before we walk up to that boundary and look at why it breaks, there is a debt to pay. Max Planck is remembered for these units, but he was not quite the first to dream them. A quieter man got there before him, building natural units from the electron, and history has nearly forgotten him. History tends to hand the whole prize to one name, and in the story of natural units that name is Planck. The units carry his name, the scale carries his name. But the idea of building units from the fundamental constants of nature did not begin with him. It began, almost 20 years earlier, with an Irish physicist named George Johnstone Stoney, and his story deserves to be told. Stoney worked in Ireland in the 1800s, and he was a careful, thoughtful scientist with one very large idea. He became convinced that electricity was not a smooth fluid, as many believed, but came in tiny indivisible units, in fixed grains of charge. This was a bold notion for the time. He even estimated the size of that basic grain of charge, the charge of what we would later call the electron, working it out from measurements of how electricity broke apart chemical compounds. And he gave the grain a name. He coined the word electron itself, the name we still use today for that fundamental particle, years before anyone actually detected it. Stoney saw something Planck would see later. He realized that nature seemed to provide a handful of constants that did not depend on human choices. He had the speed of a light. He had Newton's gravitational constant, and now he believed he had a fundamental unit of electric charge, the grain he had named. With those three, he could do exactly the kind of juggling we have described, combining them to cancel out unwanted units and leave behind a pure length, a pure time, a pure mass. In the 1870s and 1880s, Stoney built a set of natural units from these constants, and he presented them as a way to measure the world in terms that any physicist anywhere would recognize. His units were close cousins of Planck's. The main difference was the third ingredient. Stoney built his units around the charge of the electron, the grain of electricity. Planck, working later, built his around the quantum of action, his own new constant from the glowing of hot bodies. Because the two men used a different third constant, their lengths and times came out somewhat different in size, though both lived down in the same fantastically small basement of reality. The deep idea, though, the idea of letting the constants of nature define the ruler, was the same, and Stoney had it first, so why do we say Planck length and not Stoney length? Part of the answer is timing. When Stoney proposed his units, the quantum revolution had not yet happened, and the full meaning of a fundamental length was not clear. When Planck proposed his, quantum theory was being born, and his constant turned out to be one of the central numbers of all physics. Planck's units became woven into the new theories in a way Stoney's never were. Part of it, too, is simply the way history rewards the famous and overlooks the quiet. Stoney was respected in his time, but he never reached Planck's towering renown, and as the decades passed, his role faded from the common story. There is a small justice in remembering him. The Stoney units are still known to physicists, and his name still sits on the electron he christened. He reminds us that big ideas often have more than one parent, and that the person whose name sticks is not always the person who arrived first. The deep dream, a measuring stick built from the bones of the universe, belonged to Stoney before it belonged to Planck. With the units built and their history honoured, we can turn from how the numbers are made to why they mark an edge. The reason has to do with a humble, practical question that turns out to reach all the way to the bottom of the world. What does it actually take to see something very small? To understand why the world has a smaller scale, we need to think carefully about what it means to see anything at all. Seeing feels effortless. Light enters your eye, and the world appears. But seeing is a physical act, and like every physical act, it has limits, and those limits are the key to the whole puzzle. When you look at an object, you are catching light that has bounced off it. The light carries information about the thing, its shape, its edges, its colour. But light is a wave, and waves have a built-in clumsiness. A wave cannot reveal detail much finer than its own wavelength, the distance between one crest and the next. It is like trying to feel the fine engraving on a coin while wearing thick winter gloves. Your fingers are simply too coarse to catch the detail. The wavelength of light is the size of the glove. Anything much smaller than the wavelength gets smeared out, blurred away, lost. This is not a flaw in our eyes or our instruments. It is a property of waves themselves. Ordinary visible light has a wavelength of a few hundred nanometers, which is why an ordinary microscope, no matter how finely made, can never show you a single atom. An atom is far smaller than the wavelength of visible light. The light just washes over it without resolving it, the way an ocean swell rolls over a pebble on the seabed without being disturbed at all. So how do you see something smaller than the wavelength of light? You change your light. You reach for a wave with a shorter wavelength. This is the whole secret of probing the small. To see finer detail, you need a finer wave, a shorter wavelength, a smaller glove on your fingers. Visible light gives way to ultraviolet, which has a shorter wavelength and can resolve finer features. Ultraviolet gives way to X-rays, shorter still, which is why X-rays can pick out the arrangement of atoms in a crystal. To see smaller, you always need a shorter wave. And here the quantum world enters and changes everything. Because of Planck's grain and the work that followed, we know that waves and particles are two faces of the same coin. Light is both a wave and a stream of particles, the photons, and the energy of each photon is tied to its wavelength in a strict way. A long wavelength means a low energy photon, soft and gentle. A short wavelength means a high energy photon, sharp and forceful. The two cannot be separated. If you want a shorter wave to see finer detail, you are forced to use higher energy photons. There is no way around it. Sharper vision costs more energy, always. You can feel this trade-off in everyday technology. Visible light is harmless to look at. Ultraviolet, with its shorter waves and higher energy, can burn your skin. X-rays, shorter and more energetic still, can pass through your body and damage cells, which is why the technician steps behind a shield. As the wavelength shrinks and the resolution sharpens, the energy of each particle of light climbs. Seeing smaller and hitting harder are the same act. Now you can perhaps feel where this is heading. If seeing something at the Planck length requires a wavelength as small as the Planck length, then it requires photons of staggering energy, climbing all the way up toward the Planck energy we met before, the lightning bolt in a single particle. Pour that much energy into one tiny spot, and something dramatic is going to happen to the spot itself. To sharpen that intuition into a hard limit, we need the rule that governs the trade-off exactly, the principle Werner Heisenberg gave us. The trade-off between seeing small and spending energy is not just a rule of thumb. It is written into the deepest law of the quantum world, a law discovered by a young German physicist named Werner Heisenberg in the 1920s. It is called the uncertainty principle, and it is one of the strangest and most solid facts we know. Heisenberg was in his mid-20s, working in the whirlwind of new quantum ideas alongside Niels Bohr in Copenhagen when he found it. The principle says something that sounds modest and turns out to be earth-shaking. You cannot know both the exact position and the exact motion of a particle at the same time. The more precisely you pin down where a particle is, the more uncertain its motion becomes, and the more precisely you pin down its motion, the more uncertain its position becomes. There is a strict trade-off between the two, and the size of that trade-off is set once again by Planck's constant, the quantum grain. This is not a statement about clumsy instruments. It is not that we lack a fine enough tool to measure both at once. The uncertainty is built into the particle itself. A quantum object simply does not possess a perfectly sharp position and a perfectly sharp motion at the same moment. The two qualities trade against each other as a matter of principle, the way a single bedsheet that is too short cannot cover both your shoulders and your feet at once. Pull it up to cover one, and you uncover the other. Picture trying to trap a particle in an ever smaller box. The smaller the box, the more precisely you have fixed the particle's position. But the uncertainty principle insists that as the position grows sharp, the motion must grow wild. Squeeze a particle into a tiny space, and it begins to jitter furiously, its speed and energy fluctuating more and more violently the tighter you confine it. The particle resists being pinned down by thrashing harder the more you close in. A confined quantum particle is never still. It seethes. This is the exact rule behind the trade-off we met in the last step. To locate something within a tiny region, the size of the Planck length, you must confine it to that region, and confining it that tightly forces an immense uncertainty in its motion, which means an immense energy. Heisenberg's principle takes our rough intuition that seeing small costs energy and makes it precise. The energy needed to localize a particle within a region grows without limit as the region shrinks. Pin a particle to within the Planck length, and the energy involved climbs toward the Planck energy, the lightning bolt in a speck. There is a beautiful and unsettling consequence of all this. Empty space is not truly empty. Because of the uncertainty principle, the energy in any small region can never be exactly zero and perfectly still. It must always flicker. So the vacuum itself churns with tiny fluctuations, particles flashing into being and vanishing again, borrowing energy for the briefest instant the principle allows, then paying it back. The smaller the region you examine, the more violent this churning becomes. At ordinary scales, it is a gentle hum you never notice. As you approach the Planck length, the uncertainty principle promises that the churning grows ferocious. So Heisenberg gives us the engine that drives the breakdown. To look at the Planck scale, you must confine energy to the Planck scale, and the uncertainty principle says that confinement demands an enormous concentration of energy in a vanishingly small space. We are now one short step from disaster, because we know what happens when too much energy is packed into too small a space. But first we need to make the quantum limit on locating a particle concrete, and for that we turn to a length named after Arthur Compton. Heisenberg told us that pinning a particle into a small space forces a large uncertainty in its motion and energy. Let us turn that into a definite size, a specific length that marks how sharply you can ever locate a particle of a given mass. That length is called the Compton wavelength, and it is named after the American physicist Arthur Compton. In the 1920s, Compton was firing X-rays at electrons and watching how they bounced. He found that when an X-ray photon collided with an electron, the photon came away with a longer wavelength than it went in, as if it had lost some of its punch in the collision. The amount of stretching depended on the angle of the bounce in a precise way. This was strong, direct evidence that light really does come in particles, that a photon can strike an electron like one billiard ball striking another. Out of Compton's analysis came a natural length scale for any particle, built from its mass, the speed of light, and Planck's constant. We call it the Compton wavelength of that particle. Here is the meaning to carry. The Compton wavelength of a particle is roughly the smallest region into which you can sensibly squeeze it while it stays a single particle. It is the quantum blur, the fuzziness of position that a particle of a given mass simply cannot shed. Try to confine the particle into a space smaller than its Compton wavelength, and something has to give. By Heisenberg's rule, squeezing it that tightly demands so much energy that by Einstein's relation between energy and mass, you have poured in enough energy to create brand new particles, identical copies of the one you started with. Instead of one sharply located particle, you get a swarm, and you have lost track of which is which. The very act of trying to pin the particle down past its Compton wavelength conjures more particles and defeats you. Notice the crucial relationship hidden in this length. The Compton wavelength depends on the particle's mass, and it does so in reverse. A heavier particle has a shorter Compton wavelength, a smaller quantum blur, and can be located more precisely. A lighter particle has a longer Compton wavelength, a larger blur, and is fuzzier. The electron, being very light, has a relatively large quantum blur. A proton, nearly 2,000 times heavier, has a far smaller one. The more massive the particle, the tighter you can pin it. Heavier means sharper, lighter means blurrier. Keep that rule close, because it is about to collide with another rule that runs exactly the opposite way. So here is one of our two great limits, drawn clearly. The Compton wavelength is the quantum limit on smallness. It says, this is how tightly the quantum world will let you locate a chunk of matter, and the limit gets looser for light particles and tighter for heavy ones. It is a limit that comes entirely from quantum mechanics and relativity together, from Planck's grain and Einstein's speed of light, with no gravity in it at all. It is the rule of the very small and the very light. There is a second limit waiting, and it comes from the opposite end of physics, from the world of the very heavy. It is not about how tightly you can locate a particle. It is about what happens when you gather too much mass into too small a space, until gravity itself seals the region off from the rest of the universe. That second limit was found in the equations of Einstein's gravity by a man writing from the trenches of a war, and it is the radius of a black hole. The second great limit comes from gravity, and it tells us what happens when too much mass crowds into too small a space. It is called the Schwarzschild radius, and behind it lies a quiet, sad story from the middle of the First World War. In late 1915, Albert Einstein had just published his theory of gravity, the general theory of relativity. It was a sweeping new picture in which gravity is not a force pulling across empty space, but the bending of space-time itself by mass. A heavy object like the sun curves the space and time around it, and other objects like the planets simply follow the straightest paths they can through that curved geometry. The theory was beautiful, but its central equations were ferociously hard to solve. Einstein himself doubted that exact solutions would come easily. They came within months from an unexpected place. A German physicist and astronomer named Karl Schwarzschild was serving in the army on the Russian front, calculating artillery trajectories amid the cold and mud of the war. In whatever moments he could find, he worked through Einstein's new equations for the simplest case, the space-time around a single round mass. He found an exact solution, wrote it up, and sent it to Einstein, who presented it on his behalf. Schwarzschild had solved the master equations of general relativity from a war zone. Within a year he was dead, killed not by a shell but by a rare and painful autoimmune disease he contracted at the front. He never lived to see what his solution would come to mean. Buried in Schwarzschild's solution was a special distance now named after him. For any given mass, there is a particular radius, the Schwarzschild radius, with a dramatic property. If you could compress the entire mass inside a sphere of that radius, the curvature of space-time there would become so extreme that nothing could escape, not even light. The pull would be total. Any light trying to leave would be bent relentlessly back inward, and so would anything else. A region like that is what we now call a black hole, and the surface at the Schwarzschild radius is its event horizon, the point of no return. The event horizon is not a solid shell. It is a boundary in space, a one-way membrane. Cross it from outside, and you can never send any signal back out, because to do so your signal would have to outrun light, and nothing can. Whatever happens inside is sealed away from the rest of the universe forever. The horizon is the edge of the knowable, drawn by gravity alone. Now notice how the Schwarzschild radius depends on mass, because this is the key to everything that follows. The more mass you have, the larger the Schwarzschild radius, the bigger the black hole. Pile on more mass, and the event horizon swells outward. This is the exact opposite of the Compton wavelength, which shrank as mass grew. As you add mass, the quantum blur, the Compton wavelength gets smaller and tighter. At the same time, the gravitational radius, the Schwarzschild radius, gets larger. One limit pulls inward as mass rises, the other pushes outward. Two limits then, running in opposite directions as you change the mass. The quantum limit, the Compton wavelength, says how tightly you can locate a particle, and it shrinks for heavier masses. The gravitational limit, the Schwarzschild radius, says how small a region a mass can occupy before it seals itself off as a black hole, and it grows for heavier masses. For a light particle, the quantum blur is huge and the gravitational radius is laughably tiny. For a heavy mass, the gravitational radius is huge and the quantum blur is tiny. Somewhere in between, the two must cross. The place where they meet is the Planck scale, and finding it is the next decisive step. We have two limits, drawn from opposite ends of physics, and they run in opposite directions. The quantum blur, the Compton wavelength, says how tightly you can locate a particle, and it gets smaller as the particle gets heavier. The gravitational edge, the Schwarzschild radius, says how small a region a mass can occupy before it seals itself off as a black hole, and it gets larger as the mass gets heavier. One shrinks as mass rises, the other grows. Picture them as two lines on a sheet, one sloping down, one sloping up, as you read from light masses to heavy ones. Two lines that move in opposite directions must cross somewhere. The only question is where. Follow the light particle first. An electron is very light, so its quantum blur is large, a generous fuzzy region you cannot squeeze it below. Its gravitational radius, on the other hand, is almost unimaginably tiny, because so little mass bends space-time so feebly. For the electron, the quantum blur towers over the gravitational radius. The fuzziness wins by a vast margin, and gravity is a complete irrelevance. This is the ordinary world of particle physics, where gravity is so weak it can be ignored entirely, and quantum mechanics rules alone. Now walk the other way, toward heavier and heavier masses. As the mass climbs, the quantum blur shrinks, and the gravitational radius grows. The gap between them narrows from both sides at once. The fuzzy region you cannot pin below gets tighter. The black hole edge you would form by squeezing the mass gets wider. Step by step, the two close in on each other, and at one particular mass they meet. The smallest region the quantum world will let you confine the mass into is exactly the size of the region where that mass would become a black hole. The two limits land on the same length. That mass is the Planck mass, the speck of dust we met before, and that length, where the quantum blur and the gravitational edge coincide, is the Planck length. This is the real reason the Planck units mark a boundary. They are not just an arbitrary recipe of constants. They are the precise place where the rule of the very small and the rule of the very heavy meet as equals, where the fuzziness of the quantum and the curvature of gravity reach the same size at the same time. Below that meeting point, the picture turns incoherent. For a mass heavier than the Planck mass, the gravitational radius is larger than the quantum blur, which means the object is already inside its own event horizon, already a black hole, before quantum fuzziness even comes into play. For a probe sharper than the Planck length, the energy you must concentrate to achieve that sharpness, by Heisenberg's rule, is so great that it forms a black hole at the very spot you're trying to examine. Either way, gravity and the quantum stop being separable. They become the same problem, and neither theory alone can handle it. This is why physicists say the Planck length is where quantum mechanics and gravity must be married, whether we know how to perform the wedding or not. Above it, the two theories live apart and each works beautifully in its own domain. At the Planck length, they are forced into the same tiny room, and we have no theory that can describe what they do once they are in there together. The crossing point of the two limits is the doorway to the unknown. We have reached it by pure reasoning, never leaving our chairs, combining a quantum length with a gravitational length and watching them meet. But reasoning can sometimes mislead, so it is worth pressing on the conclusion directly. What actually happens, in concrete terms, if you build the finest microscope allowed by the laws of physics and aim it at the Planck length? The answer is that the microscope destroys the very thing it is trying to see. Imagine you set out to build the ultimate microscope, a machine that could resolve the Planck length itself, and follow honestly what the laws of physics would do to it. The thought experiment is one of the cleanest ways to feel why this scale is a true wall, and not just a far-off number. You will find that the closer the machine gets to its goal, the more thoroughly it ruins its own picture. Start from what we already know about seeing small. To resolve a tiny distance, you need a probe with a wavelength at least as small as that distance. To see the Planck length, you need a wavelength as short as the Planck length, and a wave that short, by the link between wavelength and energy, carries a colossal punch. The photon, or whatever particle you use as your probe, must carry an energy climbing all the way up toward the Planck energy, the lightning bolt packed into a single particle. There is no gentler way. Sharper vision demands higher energy, always, and Planck sharpness demands Planck energy. Now bring in gravity, which we usually get to ignore but cannot ignore here. You're about to deposit a Planck energy's worth of energy into a region a Planck length across, because that is what aiming your probe at that spot means. But energy, by Einstein, is a form of mass, and mass bends space-time. Concentrate that much energy into that smaller region, and you have assembled exactly the recipe for a black hole. The Schwarzschild radius of all that concentrated energy is about the Planck length itself, so at the very instant your probe reaches the resolution you wanted, the spot you're looking at collapses into a tiny black hole, and a black hole is the end of seeing. Whatever you were trying to examine vanishes behind an event horizon, sealed off from you forever. No light comes back out, no information escapes. The harder you push your microscope to see the Planck length, the more certainly you create a black hole that swallows the answer. Push even harder, with even more energy to try to see even smaller, and you do not get a sharper image. You get a bigger black hole with a wider horizon, hiding even more from view. Past the Planck length, adding energy makes the dark region grow rather than shrink. The microscope eats itself. This is the deep reason the Planck length appears to be a genuine smallest meaningful length, and not merely a practical hurdle. It is not that our tools are too weak. It is that the laws of physics themselves conspire so that any tool sharp enough to probe below the Planck length must create a black hole that destroys the measurement. The concept of a smaller distance loses its operational meaning because there is no possible experiment, even in principle, even with unlimited technology, that could ever measure it. A distance that can never be measured by anything, even in principle, may simply not be a distance at all. So the wall is not made of metal or of cost. It is made of the same physics we have been building all along, the speed of light, the quantum grain, and the weakness of gravity, all turning together to close the door. The Planck length is where the act of looking and the thing looked at become impossible to separate, where the observer's probe becomes a black hole and the question dissolves. We keep saying that our theories break down at this scale. It is time to say plainly what that means, and which two theories are quarrelling. The trouble is that the two greatest achievements of physics, when forced together at the Planck length, do not merely fall silent, they actively disagree. When physicists say that physics breaks down at the Planck scale, they are pointing to a real and specific quarrel between the two deepest theories we have. These two theories are each, on their own, among the greatest triumphs of the human mind. Each has been tested to staggering precision and never found wrong. The trouble is that they describe the world in ways that cannot both be fully true at the Planck length, and there they come to blows. The first theory is general relativity, Einstein's account of gravity. Its picture of the world is smooth. Space-time in general relativity is a continuous flowing fabric, gently curved by mass and energy. Planets glide along its valleys, light bends as it crosses its slopes, and everything happens in a graceful, unbroken geometry. The mathematics assumes you can zoom in on any point of space-time and find it smooth, like the surface of a calm pond examined ever more closely and staying ever more glassy. General relativity is a theory of the large and the heavy, of stars and galaxies and the universe as a whole, and at those scales its smooth fabric describes reality with breathtaking accuracy. The second theory is quantum mechanics, the account of the very small. Its picture of the world is the opposite of smooth. It is grainy, jittery, restless, ruled by the uncertainty principle. In the quantum world, nothing sits perfectly still, nothing has a perfectly definite value. An empty space itself churns with fluctuations, with energy flickering in and out of existence on the tiniest scales. The smaller the region you examine, the more violent this churning becomes. Quantum mechanics is a theory of the small and the light, of atoms and particles and fields, and at those scales its restless graininess describes reality with equally breathtaking accuracy. Now you can see the collision. General relativity demands a space-time that is smooth all the way down, perfectly continuous no matter how far you zoom in. Quantum mechanics insist that nothing can be smooth all the way down, that everything fluctuates, and that the fluctuations only grow wilder as you shrink the scale. At ordinary sizes there is no conflict, because the quantum churning of space-time is far too faint to matter, and the smooth picture works perfectly. The two theories live in separate kingdoms and never have to argue. At the Planck length, the kingdoms overlap, and the argument becomes unavoidable. There, the quantum fluctuations are no longer a faint background hum. They are as strong as gravity itself, strong enough to twist and tear the very fabric that general relativity insists must stay smooth. The smooth space-time of Einstein and the seething uncertainty of the quantum cannot both hold at that scale. The fabric general relativity needs is exactly the thing quantum mechanics will not allow. This is the heart of the matter. We do not have a theory of quantum gravity, a single framework in which gravity and the quantum live together in peace. We have two magnificent theories that work perfectly apart and contradict each other at the Planck length. Every attempt to simply staple them together has run into trouble, and the trouble is not a small technical wrinkle. It is woven into the foundations, into the clash between a smooth world and a grainy one. So the breakdown is not vagueness or ignorance in the ordinary sense. It is a sharp, identifiable conflict between two of the best ideas we have ever had, a conflict that only shows itself at the smallest scale. To feel why physicists cannot simply force the two together with a clever patch, we need to look at what goes wrong, concretely, when they try. The answer comes back as infinities, as equations that swell to nonsense and refuse to be tamed. When physicists try to force gravity and the quantum together with the usual tools, the equations do not just resist, they explode. The answers come back as infinities, as quantities that grow without bound and turn the whole calculation to nonsense. To understand why this is such a deep problem, and why it is special to gravity, it helps to know that physics has met infinities before, and learned to handle them, almost everywhere except here. The other forces of nature, the electromagnetic force and the two nuclear forces, all have successful quantum theories, and when those theories were first written down, they too produced infinities. Calculate something simple, like the way two electrons repel, and the early equations would hand back an infinite answer, which is plainly wrong. For a while this seemed like it might doom the whole project. Then physicists found a way through, a careful mathematical procedure for taming the infinities, called renormalization. The idea behind renormalization is subtle, but you can feel its spirit. The infinities come from the contributions of smaller and smaller scales, from the wild quantum fluctuations at ever shorter distances. Renormalization is a disciplined way of absorbing those troublesome short-distance contributions into a few measured quantities, like the mass and charge of the electron, so that everything you actually predict comes out finite and sensible. It worked spectacularly. The quantum theory of electromagnetism, tamed this way, became the most accurately tested theory in all of science, agreeing with experiment to a dozen decimal places. The infinities were not an illusion, but they could be managed. Then physicists tried the same trick on gravity, and it failed. Gravity refuses to be renormalized. When you apply the procedure that tamed the other forces, the infinities in gravity do not get absorbed into a few neat quantities. Instead, they multiply. Every time you try to mop up one infinity, you generate more, an endless cascade that no finite set of measured quantities can ever soak up. The method that rescued every other force runs aground completely on gravity. The technical name for this is that gravity is not renormalizable, and that single fact has shaped decades of theoretical physics. Why is gravity so different? The deepest reason traces back to what gravity is. The other forces act within space-time, like players moving on a fixed field. Gravity is the field. Gravity is the shape of space-time itself. So when you make gravity quantum, you are not adding jitter to particles moving on a fixed stage. You are making the stage itself jitter, making distance and time and the very geometry uncertain. The quantum fluctuations feed back on the space-time that is supposed to contain them, and the feedback grows uncontrollable at short distances. The closer you look, the worse it gets, and the infinities come pouring in faster than any patch can catch them. It is worth being honest and calm about what this does and does not mean. It does not mean our theories are worthless. Both general relativity and quantum mechanics keep working perfectly in their own domains, untouched by this failure. It means only that the simple, obvious way of combining them does not work, that nature is telling us something we have not yet understood about how gravity and the quantum fit together. The infinities are not a dead end. They are a signpost, pointing at a missing piece. Faced with this breakdown, physicists have tried to picture what space-time might actually be doing down at the Planck scale, where the smooth fabric tears. One of the first and most vivid pictures came from an American physicist with a gift for naming the unnameable, John Wheeler, who imagined the bottom of the world not as smooth and not as a tidy grid, but as a churning, restless foam. If smooth space-time cannot survive at the Planck length, what takes its place? One of the earliest and most enduring answers came from the American physicist John Archibald Wheeler, a man with a rare talent for giving vivid names to the deepest ideas. Wheeler coined the term black hole, and he also gave us a phrase for the bottom of the world. He called it space-time foam, or quantum foam, and the image has shaped how physicists imagine the Planck scale ever since. Wheeler's reasoning followed straight from the uncertainty principle. We have seen that the quantum world forbids perfect stillness, that the smaller the region you examine, the more violently its energy fluctuates. Wheeler applied this not to particles moving through space, but to the geometry of space itself. If space-time is a physical thing, and the quantum rules apply to it as they apply to everything else, then space-time too must fluctuate. And those fluctuations, harmless and invisible at ordinary scales, would grow more and more violent as you zoomed in toward the Planck length. Picture the surface of the ocean seen from a high-flying plane. From that height it looks like a smooth blue sheet, perfectly flat and calm. This is space-time as general relativity sees it, gently curved, continuous, serene. Now descend toward the water. From lower down you begin to see swells, then waves, then whitecaps, and right down at the surface, where wave meets air, there is froth, a churning chaos of bubbles forming and bursting, with no smooth surface left at all, only restless foam. Wheeler proposed that space-time is like this, smooth from far away, where we live, but foaming and turbulent when you descend all the way to the Planck length. In this foam, the very ideas we rely on would lose their footing. Distance and direction would blur. The smooth, orderly geometry of Einstein would dissolve into a seething tangle where space might briefly fold back on itself, where tiny tunnels and bridges might flicker into being and vanish, where the question of whether 2 points are near or far might have no steady answer. Wheeler even imagined that the foam might constantly sprout and swallow minuscule wormholes and warps, a geometry that would not hold still long enough to be measured. The placid fabric of space-time would be revealed as a coarse average over a frantic, ever-changing froth, the way the calm ocean surface is really an average over countless leaping molecules. It is important to hold this picture honestly, the way Wheeler himself did. The quantum foam is not an established fact. We have never seen it, and we have no complete theory that describes it, precisely because we lack the theory of quantum gravity that would tell us what the foam truly looks like. It is an educated guess, a physically motivated picture of what the breakdown of smooth space-time might mean. Some modern approaches suggest the bottom of the world is foamy in roughly Wheeler's sense. Others suggest it is something quite different. The honest statement is that we do not yet know, but the value of Wheeler's image is real. It gives us a way to think about a scale we can never visit, a way to translate the cold fact that our equations break down into something the mind can picture. When physicists say space-time loses its meaning at the Planck length, the foam is often what they have in mind, a place where the smooth stage of physics gives way to restless, bubbling uncertainty. Whether the true picture is foam or grid or something stranger, the lesson holds. The smoothness we take for granted is a large-scale illusion, and the bottom is wild. There is one place in the real universe where this wild scale was not a thought experiment, but an actual condition where the entire cosmos was squeezed to the Planck density. That place is the very beginning, the first sliver of time after the Big Bang, and it sets the oldest wall in all of science. There is one moment in the history of everything when the Planck scale was not a far-off abstraction, but the actual state of the entire universe. That moment is the beginning, the first faint sliver of time after the Big Bang, and it gives the Planck scale a role in the largest story there is, the story of where the cosmos came from. We have strong evidence that the universe began in a hot, dense state, and has been expanding and cooling ever since. Run the film backward, and everything draws together. Galaxies rush toward one another, the space between things shrinks, and the matter and energy of the cosmos grow denser and hotter the further back you go. The early universe was a furnace, and the earlier you look, the hotter and tighter it gets. Our theories let us follow this backward run with real confidence through an astonishing range, back through the formation of atoms, back through the forging of the first nuclei, back to the first tiny fractions of a second when the universe was a seething plasma of particles. But the backward run cannot continue forever. As you approach the very beginning, the universe becomes so dense and so hot that you reach the Planck scale, the entire observable cosmos squeezed into a region governed by Planck density and Planck temperature. And at that point, the same breakdown we have been tracing brings the film to a halt. When the universe was about 1 Planck time old, roughly the shortest meaningful tick there is, the whole of it was a place where gravity and the quantum were equally strong, where smooth space-time could not hold. To describe the universe at that age, you would need the theory of quantum gravity that we do not have. This earliest interval is called the Planck epoch, and it is the oldest wall in cosmology. We can describe the universe from 1 Planck time onward, with increasing confidence as it expands and cools. We cannot honestly describe what happened during that first Planck time, or what, if anything, came before it. Our equations run back into the Planck epoch, stop giving trustworthy answers, and start giving the same infinities and nonsense we met before. The beginning of the universe is hidden behind the very same breakdown that hides the bottom of a black hole. Because they are the same breakdown, the Planck scale reached in time rather than in space. This is a humbling place to stand. The question of how the universe began, perhaps the oldest question human beings have ever asked, runs straight into the Planck wall. To answer it, to say what the cosmos was doing in its very first instant, we would need to understand how gravity and the quantum unite. The origin of everything and the smallest scale of everything turn out to be the same problem wearing 2 different faces. The theory that would tell us what lies below the Planck length would also tell us what lies at the dawn of time. There is something fitting in this. The largest question, the birth of the universe, and the smallest question, the bottom of space, are locked together. You cannot answer one without answering the other. The walk down to the smallest scale and the walk back to the first moment lead to the same closed door, and behind that door is the missing theory. We cannot visit the Planck epoch, and we cannot build a microscope to reach the Planck length, but nature has built one laboratory where gravity and the quantum are forced to deal with each other, an object we can actually study from a safe distance. That laboratory is the black hole, and what it taught us came as a complete surprise. If we cannot reach the Planck scale in a machine or revisit the first instant of time, we need some other place where gravity and the quantum are forced to deal with each other, somewhere we can study from afar. Nature provides exactly one such laboratory, and it is the black hole. For a long time, black holes seemed to belong wholly to gravity, to be pure creatures of curved space-time with nothing quantum about them. Then two physicists working in the 1970s showed that black holes are where gravity and the quantum are quietly already entangled, and the discovery reshaped the whole field. The first clue came from a young researcher named Jacob Bekenstein. He was thinking about a puzzle. Physics has a cherished law, the second law of thermodynamics, which says that disorder, measured by a quantity called entropy, always tends to increase. Drop a hot cup into a cold room, and the heat spreads out, never to gather itself back. But what happens if you drop something disordered into a black hole? The black hole swallows it, and from outside the black hole looks featureless, described by just its mass and a couple of other numbers. The disorder seems to vanish, which would violate the sacred law. Bekenstein made a daring proposal to save it. He suggested that a black hole must itself have entropy, a measure of hidden disorder, and that this entropy is proportional to the area of its event horizon. The bigger the horizon, the more hidden disorder it holds. This was a strange and beautiful idea, that the surface area of a black hole measures the information it has swallowed. But it carried a troubling implication. Anything with entropy and a relationship to energy should have a temperature, and anything with a temperature should glow, should radiate energy away. Yet a black hole, by its very definition, was supposed to let nothing escape. The idea seemed to contradict itself, and many physicists doubted it. The resolution came from the British physicist Stephen Hawking, who set out partly to prove Bekenstein wrong, and ended up proving something stranger than either of them expected. Hawking applied quantum mechanics to the empty space just outside a black hole's horizon, the seething vacuum we met before, where particles flicker constantly in and out of existence. He found that the intense gravity at the horizon can split these fleeting pairs, capturing one partner and letting the other escape. To a distant observer, the black hole appears to glow faintly, radiating a thin stream of particles. We now call it Hawking radiation. Black holes are not perfectly black after all. They are warm, and they slowly evaporate. This was a watershed. Hawking's result joined gravity in the curved space-time of the horizon with the quantum in the flickering vacuum, and produced something neither could give alone, a temperature for a black hole and a way for it to leak away. It confirmed Bekenstein's guess that the horizon's area measures entropy, and it did so by forcing relativity and quantum mechanics to work together. For the first time, a real calculation reached into the territory of quantum gravity and came back with a concrete, agreed-upon answer. And the answer pointed straight at the Planck scale. When you count the hidden disorder of a black hole, the natural unit that appears is the Planck area, the Planck length squared. The horizon behaves as though it were tiled with tiny patches, each about 1 Planck area in size, each holding a single basic unit of information. The black hole's entropy is, in effect, the number of Planck-sized tiles it would take to cover its horizon. The Planck length had walked in through a side door as the size of the pixels of a black hole's memory. That counting of tiles on a surface carried a hint so strange it took years to absorb. The information inside a black hole seems to be measured not by its volume but by its surface, and that clue grew into one of the boldest ideas in modern physics, the holographic principle. The black hole's strangest lesson was not the radiation, or even the temperature. It was a quiet fact about where the information lives, and it led to one of the boldest ideas in modern physics, an idea called the holographic principle. To feel its force, hold on to the surprise hidden in Bekenstein and Hawking's result. The amount of information a black hole can hold is set by the area of its horizon, the two-dimensional surface, not by the volume inside. Stop and weigh how odd that is. Everywhere else in life, the amount a container can hold depends on its volume. A bigger box holds more, double the box in every direction, and you expect it to hold 8 times as much because volume grows with the cube of size. But a black hole does not work this way. Double its size and the information it can hold grows only with its surface area, with the square of size, not the cube. It is as though the contents of a room were limited not by the space inside it, but by the area of its walls. The interior, the volume, seems to hold less than you would ever expect. The real accounting happens on the boundary. Two physicists, the Dutch theorist Gerard 't Hooft and the American theorist Leonard Susskind, took this peculiarity and pushed it to a radical conclusion. If the maximum information in any region is set by the area of its boundary rather than its volume, perhaps that is telling us something deep about reality itself. Perhaps everything happening inside a region of space can be fully described by information living on the surface that surrounds it. The three-dimensional world inside, with all its depth and richness, might be encoded on a two-dimensional boundary, the way a flat hologram on a card can store a full three-dimensional image. This is the holographic principle, and the name comes from exactly that comparison. A hologram is a flat piece of film that, when lit correctly, shows a three-dimensional scene with real depth. The depth is an illusion conjured from information stored on a surface. 't Hooft and Susskind proposed that our universe might be holographic in the same sense, that the familiar three-dimensional world we move through could be, in some precise way, a projection of information written on a distant two-dimensional surface. The volume we feel ourselves inhabiting might be the conjured depth, and the true accounting might live on a boundary. The pixels of that surface, the smallest patches of information on the holographic boundary, are once again Planck-sized. The principle says, in effect, that the world stores about 1 unit of information per Planck area of bounding surface, and no more. The Planck length sets the resolution of reality's deepest description, the size of the smallest meaningful pixel on the cosmic film. It is the same Planck length we built from 3 constants long ago, now reappearing as the grain of a holographic universe. The holographic principle remains a principle, not a finished theory, but it has proven extraordinarily fruitful. In certain carefully defined model universes, physicists have found exact working examples where a three-dimensional world with gravity is perfectly mirrored by a two-dimensional world without gravity living on its boundary. These examples are among the strongest hints we have that gravity and the quantum can be united, because in them the union actually happens, in a toy setting we can calculate. They suggest that space-time and gravity themselves might not be fundamental at all, but might emerge from something deeper, a pattern of information on a surface. This idea of emergence, that space and gravity grow out of something more basic, runs through every serious attempt to reach the Planck scale. The 2 leading attempts take that idea in very different directions. The first proposes that the fundamental things are not points at all, but tiny vibrating strings, and that a smaller size is built into the world from the start. The first of the 2 leading attempts to reach below the Planck scale begins by questioning something so basic we rarely think to doubt it. In all of ordinary physics, the fundamental particles, the electron, the quarks, the photon, are treated as points, as objects with no size at all, located at a single mathematical spot in space. String theory proposes that this is wrong. It says that if you could zoom in far enough, you would find that each particle is not a point but a tiny vibrating string, a minuscule loop or strand of energy, and that this single change cures the breakdown at the Planck scale. The motivating idea is elegant. We have seen that the infinities of quantum gravity come from the wild behavior at ever shorter distances, from forcing point particles to interact at a single sharp location where the fluctuations grow uncontrollable. A point has no size, so 2 points can be brought arbitrarily close together, all the way down to 0 separation, and it is in that limit of 0 distance that the infinities erupt. String theory's answer is to abolish the point. If the fundamental objects have a size, a smallest extent set near the Planck length, then nothing can ever be brought truly to 0 separation. The string's own size smears out the dangerous short-distance behavior, and the infinities that wreck ordinary quantum gravity are gently softened away. The strings are unimaginably small, about the Planck length in extent, which is why every particle we have ever measured still looks like a perfect point. We are far too coarse to see the string. But the theory makes a striking claim about what the different particles are. A string can vibrate in different patterns, different modes, the way a guitar string can sound different notes. In string theory, each pattern of vibration is a different particle. One mode is an electron, another a quark, another a photon. The whole zoo of particles becomes a single kind of object, a string, playing different notes. The universe, in this picture, is something like music, with the variety of matter arising from the harmonies of vibrating strands. String theory has a feature that thrills some physicists and troubles others. To make the mathematics consistent, the strings must vibrate not in the 3 dimensions of space we know, but in many more, with the extra dimensions curled up so small that we never notice them, smaller even than the strings themselves. The theory also naturally contains gravity. When physicists worked out the possible vibration patterns, one of them turned out to have exactly the properties of the particle that would carry the gravitational force. Gravity was not put in by hand. It fell out of the theory unbidden, which many took as a powerful sign that string theory was on the right track to unite gravity with the quantum. For these reasons, string theory became the most intensively studied approach to quantum gravity, occupying thousands of physicists for decades. It offers a vision where a smaller size is built into reality from the beginning, where the Planck length is the scale of the strings, and where the breakdown of physics is healed by replacing points with extended vibrating objects. But string theory has not been confirmed. Its strings and extra dimensions lie far beyond any experiment we can perform, and the theory comes in a bewildering number of possible versions, with no clear way yet to pick the one that describes our world. It remains a beautiful, unproven possibility, and it is not the only one. A rival approach takes the opposite path, leaving particles as points, but making space itself the thing that comes in smallest pieces. The second great attempt to reach below the Planck scale takes the opposite path from string theory. Where string theory keeps space smooth and gives particles a size, this approach keeps particles as points and makes space itself grainy. It is called loop quantum gravity, and it grew from the work of physicists including the Italian theorist Carlo Rovelli and the American theorist Lee Smolin. Its central claim is bold and simple. Space is not a smooth, continuous backdrop. Space is made of pieces, woven from tiny indivisible chunks, and the Planck length is the size of the weave. To feel the idea, think about how the other quantities in physics turned out to come in chunks. Energy, once thought smooth, comes in quanta, the grains Planck discovered. Electric charge comes in fixed units. Loop quantum gravity asks the natural next question. What if space itself is quantized in the same way? What if area and volume, the very measures of space, cannot take any value at all, but come only in discrete steps, with a smallest possible area and a smallest possible volume, both near the Planck scale? In this picture, you cannot have a region of space smaller than the smallest chunk, just as you cannot have less charge than a single electron's worth. Space has a finest grain, and below it there is no smaller space to speak of. The mathematics builds space-time out of a network, a web of connected nodes and links that Rovelli and Smolin and their colleagues call a spin network. Each node carries a tiny quantum of volume, and each link a tiny quantum of area, and the whole network is the true fine-grained structure of space. What we experience as smooth, continuous space is this network seen from far away, the way a piece of woven cloth looks like a smooth sheet until you bring it close and see the separate threads. Run the network forward in time and it becomes a kind of foam of its own, a structured version of Wheeler's churning bottom, built not from chaos but from a precise weave of quantized space. Loop quantum gravity has a feature that sets it apart from string theory. It does not require extra dimensions, and it does not require replacing particles with strings. It starts directly from Einstein's general relativity, and applies the rules of the quantum to it, to space-time itself, trying to quantize gravity on its own terms rather than folding it into a larger theory of everything. Its ambition is narrower than string theories. It does not try to explain all the particles and forces in one stroke. It tries to do one thing, to make a sensible quantum theory of space-time and to show that space at the bottom is discrete. The approach has had real successes inside its own framework. It produces a smallest area and a smallest volume cleanly, giving a concrete meaning to the idea that space is grainy at the Planck scale. It has been used to model what might happen at the centre of a black hole and at the beginning of the universe, where the grain of space might replace the infinite densities that plague the smooth theory, smoothing the Big Bang into something more like a bounce. Like string theory, though, loop quantum gravity remains unconfirmed, far beyond the reach of experiment, and it faces deep, open questions of its own, including how to recover ordinary smooth space-time cleanly in the everyday limit. We now have two rival pictures of the bottom of the world, one of strings in a smooth space, one of a space woven from chunks, and they disagree on the most basic question of all. We have arrived at a genuine fork, and it is worth standing at it honestly, because the two leading theories of the Planck scale give opposite answers to the simplest question we can ask. Is space, at the very bottom, smooth or grainy? Is it a continuous fabric that goes on forever as you zoom in? Or is it chopped into smallest pieces below which there is nothing finer? This is not a small disagreement about details. It is a disagreement about the basic nature of space itself, and we do not yet know which side is right. On one side stands the grainy picture. Loop quantum gravity says space comes in chunks, with a smallest area and a smallest volume near the Planck scale. In this view, the Planck length is real and physical, an actual smallest size, the edge of a discrete weave. Space would be like a digital image, which looks smooth from a distance but resolves into separate pixels when you look closely enough, with nothing in between the pixels. The continuous space of our everyday experience would be an illusion, a large-scale average over a fundamentally discrete structure. The bottom of the world would be a grid, or a weave, or a network, but in any case a thing made of countable pieces. On the other side stands the smooth picture. String theory, for the most part, keeps space continuous. The Planck length appears not as the size of a pixel of space, but as the size of the strings, and as the scale where new physics, like extra dimensions, comes into play. Space itself, in this view, can still be subdivided without end, even though the objects living in it have a smallest size, and the physics changes character at the Planck scale. Here the Planck length marks a threshold where the rules change, not a smallest possible distance below which space ceases to exist. Both pictures agree that something dramatic happens at the Planck length. Both agree that our ordinary notion of smooth, infinitely divisible space cannot simply be carried all the way down unchanged. But they disagree on the deepest point, on whether the smaller scale is a true floor made of discrete pieces or a threshold in a space that remains continuous. And there are still other approaches, less developed, that paint yet other pictures, some in which space-time itself is not fundamental at all, but emerges from something with no geometry in it whatsoever, no space and no time, only relationships from which space and time somehow arise. The honest situation is that we do not know. We have several beautiful, serious, mathematically rich proposals, and no way yet to tell which, if any, describes our universe. This is not a comfortable place for science to stand, but it is a real one, and the calm response is to say it plainly. The question of whether space is smooth or grainy at the Planck scale is open. We can describe the rival answers, we can admire their elegance, but we cannot yet point to the true one, because the experiment that would decide between them is the very experiment we have shown to be impossible, the one that would require building a black hole to see the Planck length. That word impossible deserves a closer look, because it raises the obvious practical question. Just how far are we, really, from reaching the Planck scale with the machines we can actually build? The answer puts the whole problem in a sobering light, and it begins with the largest scientific instrument humanity has ever constructed. It is fair to ask, after all this talk of theories beyond reach, just how far our actual machines fall short. We have the largest, most powerful scientific instrument ever built, a machine designed expressly to probe the smallest scales of matter. Setting its reach against the Planck scale gives the clearest possible measure of the gap, and the result is humbling in a way that is worth feeling concretely rather than waving away. The machine is the Large Hadron Collider, a ring buried underground near Geneva, on the border between Switzerland and France. It is about 27 kilometers around, a circular tunnel large enough to take a city's commuter line, and it is cooled to colder than deep space so that its powerful magnets can work. Inside it, protons are whipped around the ring close to the speed of light and slammed into one another head-on. In those collisions, the energy of motion turns into a spray of new particles, and by studying that spray, physicists probe the structure of matter at scales far smaller than the proton. This is the instrument that found the long-sought particle tied to how other particles get their mass, the crowning confirmation of decades of theory. The Large Hadron Collider reaches the smallest distances we have ever directly probed, and yet it is nowhere near the Planck length. To probe a distance, recall, you need energy, and the energy this machine puts into each collision, enormous as it is by human standards, falls short of the Planck energy by a staggering factor, about 1,000 trillion. The collider resolves distances that are still about that same factor larger than the Planck length. We have not closed in on the Planck scale. We have barely taken a single step toward it across a chasm of 15 orders of magnitude. Let me make that gap physical, because a number that large slips through the mind. Suppose you wanted to build a collider powerful enough to reach the Planck energy directly, using the same technology, the same kind of ring with the same kind of magnets, just scaled up. How big would the ring have to be? The answer is that it would have to be roughly the size of the orbit of a planet, a ring not 27 kilometers around but light years around, larger than entire solar systems, perhaps as large as the galaxy. There is no foreseeable technology, no plausible amount of money or material or time that could build such a thing. The direct route to the Planck scale is not merely expensive, it is, for any civilization remotely like ours, flatly impossible. This is the sober reality behind all the elegant theories. The strings, the spin networks, the foam, the holographic surfaces, all of them describe a realm that no experiment we can build will ever reach by brute force. The scale where physics breaks down is sealed off from us not only by the black hole barrier we found earlier, the one that turns any sharp enough probe into a black hole, but also by sheer practical remoteness, the absurd amount of energy that would have to be concentrated to get there. The Planck scale is doubly hidden, by principle and by practice. It would be easy to end on despair, to say that the bottom of the world is simply beyond us and leave it there. But physicists are more resourceful than that, and the situation is not quite as hopeless as the collider comparison suggests. If we cannot reach the Planck scale by force, perhaps we can catch a faint echo of it by patience, by watching the universe very carefully for the tiniest traces that Planck scale physics might leave on things we can actually see. That hope drives a quieter kind of experiment, one that listens rather than smashes. If brute force can never reach the Planck scale, the remaining hope is subtler. Perhaps Planck scale physics, though it lives at distances we can never directly probe, leaves faint fingerprints on things we can observe, tiny effects that build up over enormous distances or accumulate over cosmic time until they grow just large enough to catch. This is the strategy of indirect detection, and it has turned the search for quantum gravity from a purely theoretical exercise into something with a thread, however thin, connecting it to real observation. The central idea rests on a possibility we have already met. If space is grainy at the Planck scale, if it has a discrete structure rather than a perfectly smooth one, then light passing through it might be very slightly affected by the graininess. In a perfectly smooth space, all light travels at exactly the same speed regardless of its colour or energy. But in a grainy space, the texture might nudge high-energy light just barely differently from low-energy light, so that photons of different energies travel at imperceptibly different speeds. Over a short trip, the difference would be far too small to notice, but over a vast enough distance, it might accumulate into a measurable lag. This is where the universe lends us a hand, by providing both immense distances and violent flashes of light. Far across the cosmos, billions of light years away, there are catastrophic explosions called gamma-ray bursts, brief and brilliant outpourings of high-energy light from dying stars and colliding remnants. The light from such a burst travels for billions of years before reaching our telescopes. If Planck-scale graininess makes high-energy photons run even slightly behind low-energy ones, then in a single burst the most energetic light should arrive a tiny bit later than the gentler light, having fallen behind by a hair on every Planck-sized step of an enormously long road. Astronomers have searched the light of distant gamma-ray bursts for exactly this kind of staggered arrival. There is a second related avenue, involving the highest energy particles in nature. Space is constantly crossed by cosmic rays, particles flung at us from violent events across the galaxy and beyond, some carrying far more energy than anything our colliders can produce. If the structure of space at the Planck scale subtly changes the rules for such extreme particles, it might alter how far they can travel or how they interact along the way, leaving a signature in the spectrum of cosmic rays that reach the Earth. Physicists comb through this data too, looking for any small deviation that Planck-scale physics might explain. So far, these searches have found no confirmed effect. The light from distant gamma-ray bursts arrives, as far as we can tell, with its different colours essentially together, with no clear sign of the staggering that grainy space would produce. The cosmic rays show no firm fingerprint of Planck-scale physics. This sounds like a disappointment, and in one sense it is, but it is also genuinely useful. A non-detection is not nothing. It rules out certain versions of the theories, telling us that if space is grainy, its graininess must be subtle enough to escape these particular tests. The simplest, most naive pictures of grainy space, the ones that would have produced an obvious effect, are already excluded by the steady arrival of distant light. This is how the question stays connected to evidence, even though the scale itself is forever out of direct reach. We cannot build the microscope, but we can let the whole universe serve as our instrument, watching its most distant and violent light for the smallest hint of the grain at the bottom. The hint has not come, but the watching continues, and in the meantime, even without a finished theory, there are things we remain confident are true, principles that any correct theory of the Planck scale will almost certainly have to honour. It would be a mistake to come away from all this thinking that we know nothing about the Planck scale, that it is pure darkness. We do not have a finished theory, and we cannot run the experiments we would most like to run. But across decades of work, certain principles have proven so robust, so deeply woven into everything that works, that physicists are confident any correct theory of the bottom must respect them. These are the things we still trust even as we fall past the edge of the map, and naming them turns the unknown from a void into a shape with known boundaries. The first survivor is the constancy of the speed of light, and the marriage of space and time that comes with it. Every theory of quantum gravity that physicists take seriously is built to preserve, at least in the everyday world we can test, the rule that the speed of light is the same for everyone, and that space and time are aspects of one space-time. The searches through distant gamma-ray bursts are, in part, tests of whether this rule bends at the Planck scale, and so far it has held. Whatever the bottom is made of, it must give back this principle when you climb away from it to ordinary scales, because that principle is confirmed to extraordinary precision. The second survivor is the quantum nature of the world, with its uncertainty and its grain of action. No serious approach to the Planck scale abandons quantum mechanics. If anything, the lesson of the black hole and the holographic principle is that the quantum runs even deeper than we thought, reaching into the structure of space-time itself. Planck's constant, the grain we met near the start, is not expected to fail at the bottom. It is expected to rule there more completely than anywhere. The third survivor is the conservation of energy and the careful bookkeeping of information. The whole drama of black hole entropy and Hawking radiation was, at its heart, a struggle to make sure that nothing is truly lost, that the universe keeps honest accounts even when matter falls behind an event horizon. The strong expectation that emerged, hard-won and now widely held, is that information is never simply destroyed, that even a black hole, as it evaporates, must somehow return what it swallowed. Any theory of the Planck scale will have to keep these books balanced. The fourth survivor is the link between gravity and the shape of space-time, the core insight of general relativity. Even the theories that make space-time emerge from something deeper still must reproduce Einstein's picture in the large, must give back curved space-time and its gravity as the everyday face of whatever lies beneath. General relativity is too well tested, too precisely confirmed by everything from planetary orbits to the bending of starlight to the ripples we now detect from colliding black holes, to be simply wrong. It can be incomplete, an approximation to something deeper, but it cannot be discarded. These survivors matter because they keep the search honest and bounded. The theory of quantum gravity is not free to be anything at all. It must reduce to relativity, and the quantum in the world we know, conserve energy, keep information, and honour the speed of light. The unknown at the bottom is hemmed in on every side by what we already trust. We are not staring into total darkness. We are looking into a region whose edges are lit by principles we're sure of, trying to make out the shape in the middle. Holding both the trusted principles and the open questions together points to a calm and powerful way of understanding what physics itself is and what it means for a theory to break down. The lesson is that every theory we have is a map with an edge, good within its borders and silent beyond them. There is a way of understanding the whole story that drains the fear from the phrase physics breaks down and replaces it with something steadier, even reassuring. It is one of the deepest lessons modern physics has learned about itself, and it is the idea of an effective theory. Once you see physics this way, the breakdown at the Planck scale stops looking like a failure and starts looking like exactly what should happen, a sign that the system is working as it should. An effective theory is a description of nature that works beautifully within a certain range of scales and is honest about having a boundary beyond which it no longer applies. Think of a map. A street map of a city is wonderfully accurate for finding your way between buildings, but it tells you nothing about the curvature of the Earth, and if you tried to use it to sail across an ocean, it would fail completely. That is not a flaw in the street map. The map is simply built for one scale, and it has an edge. Beyond that edge, you need a different map, a different description suited to the larger scale. No single map serves every purpose, and a good map maker knows the limits of the map. Physics, it turns out, is built from maps like these, nested inside one another. The physics of everyday objects is one map, superbly accurate for bridges and baseballs, silent about atoms. The physics of atoms is another map, quantum mechanics, which takes over where the everyday map goes quiet. The physics of particles is another still. Each map works within its range and hands off to a finer map when you cross into a smaller scale. And crucially, each map carries within it a hint of where its own edge lies, a scale at which its description will stop making sense and a new one will be needed. Seen this way, general relativity and quantum field theory are both effective theories, both magnificent maps with known ranges. And the Planck length is, quite precisely, the edge of our current maps. It is the scale at which general relativity, the map of smooth space-time, and quantum mechanics, the map of the grainy small, both reach their borders at once and hand off to a finer map we have not yet drawn. The breakdown at the Planck scale is the two maps reaching their shared edge. It is not the universe failing. It is our descriptions announcing honestly that here a deeper one is required. This reframing matters because it tells us the infinities and the nonsense are not signs that physics is broken, or that reality is incoherent. They are signs that we are using a map past its edge, asking the street map about the ocean, The appearance of nonsense is the map's way of telling us we have left its territory. A wiser map, the theory of quantum gravity, would give sensible answers where ours give infinities, just as the globe gives sensible answers where the street map gives nonsense. The breakdown points the way to the better map rather than denying that one exists. There is real comfort and real humility in this view together. The comfort is that the universe is not incoherent at the bottom. There is almost certainly a sensible, deeper description. The humility is that we have not found it, and that every theory we will ever have may be just another effective map with its own edge, another good description of a range of scales beyond which yet finer structure waits. Physics, in this light, is not a march toward a final, complete answer that ends all questions. It is a steady refinement of maps, each truer and finer than the last, each honest about its limits. With that calm understanding in hand, we can return at last to the question we opened with, the oldest question of all, and answer it as plainly as the physics allows. We began with a sheet of paper and a pair of hands, tearing it in half, then in half again, with the feeling that the cutting could go on forever. We can return to that paper now, having walked all the way down to the bottom of the world, and answer the question we started with. Is there a last door? Is there a smallest size past which the word smaller stops meaning anything at all? The honest answer, the one the physics actually supports, is yes, there appears to be a bottom, and it sits at the Planck length. Not because our rulers are too crude, and not because we have failed to look harder, but because the laws of the universe themselves close the door. We built the Planck length from three plain facts: the speed of light, the weakness of gravity, and the grain of the quantum, and we found that it is the one length where the rule of the very small and the rule of the very heavy meet as equals. We found that any attempt to probe below it must concentrate so much energy in so small a space that it forms a black hole and hides the answer. We found that our two greatest theories, the smooth space-time of gravity and the restless jitter of the quantum, contradict each other there and dissolve into infinities. Below the Planck length, the very idea of distance seems to lose its meaning, because no possible measurement could ever reach it. So the imagined endless cutting does stop, or at least the meaning of it does. You cannot keep halving forever. Somewhere down past the atom, past the proton, far below anything we will ever touch, the familiar ideas of here and there, of near and far, of a definite point in space, come apart. The last door is real, even if we cannot open it, even if we do not yet know what lies on the other side. But notice what kind of answer this is. We did not find the bottom by reaching it. We found it by reasoning, by taking the constants of nature at their word and following them honestly to their conclusion, the way you might learn the height of a mountain from the length of its shadow without ever climbing it. We found a boundary not just to the world, but to our own description of it, the edge of our maps, the place where our finest theories go quiet and a deeper one is needed. The Planck scale is where physics, as we have it, ends, and where the physics we do not yet have begins. And that is not a sad place to end. It is one of the most remarkable facts about being a thinking creature in this universe. We are made of atoms, which are made of smaller things still, and we live our whole lives at a scale fantastically far above the bottom of the world. Yet from up here, with nothing but careful measurement and patient reasoning, we have been able to point to the floor of reality, to name it, to calculate its size, and to understand why we cannot pass it. We have located the edge of the knowable, and felt at that edge the presence of a deeper order we have not yet grasped. The paper in your hands is made of the same stuff as the stars, woven from the same fabric whose smallest threads we have been chasing. When you tear it, you're working at the surface of a world that goes down and down and down until it reaches a bottom you can reason your way to but never touch. That bottom is the Planck length. It is the last door, and the fact that beings like us, brief and small, can stand so far above it and still know it is there, is one of the quietest wonders the universe allows.